Good afternoon, everyone. It's my great honor and privilege to introduce this year's H. Bolton Seed Lecturer, Professor Ahmed Elgamal of University of California, San Diego. Before I do that, let me say a few words about myself. I am Ahmed Elgamal. I'm a lead geotechnical engineer in WSP in Orange County, Southern California. And I've had the fortune of being one of Professor Elgamal's PhD students. I had to leave the warm California weather to come here today, but I couldn't pass up the opportunity and a chance to present him or introduce him for this prestigious award on behalf of all of his students and collaborators. So Ahmed obtained his bachelor's from University of Cairo, and upon his graduation, his advisors and mentors there told him he should consider going to Princeton so he can study soil mechanics under the famous Professor Grigory Chebotaryov. By the time Ahmed got to Princeton, Professor Chebotaryov had long retired, so he ended up studying plasticity and soil dynamics and earthquake engineering with Professors John Prevost and Ahmed Abdel Ghaffar. And if you're following, this makes me like Ahmed III in this kind of line of academic lineage. So following his master's and then PhD at Princeton, he moved to Caltech as a research fellow, working with Professors John Hall and Ron Scott. And this is when he finally got a glimpse of that very good California weather. After Caltech, he joined Rensselaer Polytechnic Institute as an assistant professor. And at RPI, he was instrumental in developing the centrifuge facility, and where he served also as technical director for the facility. After RPI, he moved to Columbia University and then to the University of California, San Diego, at a time where UC San Diego was inundated with earthquake engineering research following the California earthquakes of '89 and '94. Or it could have been just the good weather there. He's been with UC San Diego ever since for the last 28 years, and he's now a distinguished professor at the Department of Structural Engineering. Today, Professor Elgamal is a recognized leader in geotechnical earthquake engineering. His area of expertise have included large-scale computational geomechanics, development of innovative soil constitutive models, with particular emphasis on seismically induced liquefaction, large-scale experimental testing, soil structure interaction, and their interpretation of recorded seismic response for system identification and data mining techniques. He has more than 400 peer-reviewed technical publications, and he has served as editor-in-chief of the Soil Dynamics and Earthquake Engineering Journal from 2010 till 2020. In preparation for this introduction, I reached out to some of his PhD students and it turned into like a reunion chat of sorts. But I wanted to share a few notable life lessons that kept coming up. If you plan on working 80 hours a week, it's better to do it in a place with a good weather and an ocean view. Of course, you can't beat San Diego at that. Second point, inform the local police if you're planning on instrumenting a bridge, especially if it crosses an interstate. When presenting, you need to obsessively care about the reader and what they take away from your work. Share your work so that everyone can use it, and a lot of the tools developed by him and his teams are open source so that everyone can use. Finally, enjoy your life and your profession. We all have a lot of good memories with him, and whether it was working in the lab or many of the research discussions that we have while kayaking in the Pacific. He is a water sports enthusiast, and he loves all the water-related activities. So he was not only my PhD advisor, but he also taught me sailing. And before our first sailing lesson, he sent me like a sketch that he made, and he kind of like summarized sailing into like one figure. And this is kind of like my sailing reference, kind of like up to this point. Other very fond memories with him, and there's been like a time I remember where I got stranded on his jet ski in the middle of the Pacific, and he actually had to kayak out, and so he can help me out. Long story. So the H. Bolton Seed Lecture series celebrates individuals who have made profound and leading contributions to the soil mechanics and geotechnical earthquake engineering. It's one of the highest recognitions in our field, and honoring the legacy of the late Professor Seed, whose groundbreaking work in geotechnical earthquake engineering continues to influence generations of engineers and researchers. Given this prestigious tradition, it is only fitting that today's speaker is someone whose 4-decade-long career embodies these principles. And despite all his accomplishments, he has maintained a remarkable intellectual humility. He's among the most admired geotechnical faculty in the US, and not just because of his scientific contributions, but also due to his kindness and generosity towards the new generations of aspiring engineers. Today, we have the privilege of hearing from a scholar and a mentor and a leader whose work continues to shape the way we approach seismic resilience. So please join me in welcoming Professor Ahmed Elgamal as he delivers the 2025 H. Bolton Seed Lecture.
Great job.
Yeah.
Great job. Thank you.
Yeah, of course.
One sec. Thank you. Okay. Thank you.
Okay.
Thank you. Thank you very much. He did a great job. Now I put my glasses back on. Where is the middle one? It's coming up? Only on the sides? But how can I point now? This pointer won't, I have to turn this way maybe? The pointer isn't working either. Okay, thank you. Okay, excellent. Well, thank you everyone for joining us on this occasion. Of course, I'm the happiest person around, but I hope you'll also enjoy your time listening to my lecture. The title of this presentation is meant to emphasize the role of data sets in shaping my own research career. While the sensor networks in this presentation are relatively simple, the horizon today, as you all know, is virtually limitless. And the findings that we will harvest are also limitless likewise. Over my entire career, I have been blessed and privileged to work and interact with great, highly talented people. Students, mentors, researchers, practitioners, as well as wonderful colleagues who also became lifelong friends and supporters, with many among us today here in the audience, which is a source of immense pleasure for me, of course. The research that I will present today is my students' work. In this regard, I am so grateful that my nomination for the Seed Medal was started by them. This will always remain a source of much happiness for me. I am also very grateful to everyone who supported my career throughout, including the colleagues who nominated me and the colleagues who selected me from the ASCE Soil Dynamics and Awards committees. Many, many thanks to everyone. Before I start, I must say that this is an honor for my whole family, my late parents, my wife, my 2 daughters, my son-in-law, and our very, very new granddaughter. I love you all very much. they are watching us, I think, over the internet. I can't begin to describe the honor and privilege of receiving the Seed Medal. Prior recipients have shaped the field of geotechnical earthquake engineering. It is indeed a lifetime honor to join this esteemed cohort. It goes also without saying that research builds on prior research. As such, I would like to acknowledge other researchers who are not mentioned here by name, but have initiated, paved the way, and inspired. In many cases, they are now further advancing the research frontiers well beyond the scope of what will be presented today. As we all know, Professor Seed was the world's researcher and consultant in the general field of geotechnical earthquake engineering. In 1984, Professor Seed worked with Woodward-Clyde colleagues to assess the seismic response of the Aswan High Dam, which was and remains the cornerstone of modern Egyptian agriculture and power generation. It is a large rock-filled dam, as you see, and the interesting challenge at the time was to render a judgment, and this is according to Professor Idris, with no direct soil property data, no sensor network recording, but solely on the basis of sound engineering judgment. Professor Seed was the world authority and indeed uniquely qualified to undertake this challenge. A year after that, a large earthquake occurred in Mexico, as you might know, in 1985. A rock-filled dam was also affected in this earthquake, but in this case, we had data from inclinometers, from surface reference points, and from strong motion instruments to measure accelerations. And also data recorded over 10 years from 6 different earthquakes. This is a cross-section of the dam, where, as you might notice, this blue round thing is, I put it there as a symbol for an accelerometer or a strong motion instrument that was on the downstream slope of this dam. And along with the other instrumentation, it recorded accelerations from all the earthquakes that had occurred over the years. And as you see here on the left side of this slide, all of these earthquake records, year in, year out, show asymmetric response with positive values much greater than negative values in the 75 events, the 79 events, the 81 event, and the 85 event. So when we started looking at this, of course, this was peculiar. And then we started thinking, well, maybe this is related to a yield acceleration that is causing these negative values not to be as high as the positive values. And if that would be the case, then as you see, this yield acceleration would cause permanent displacements to be taking place. So we started going to the other sensors that we had to see if, in fact, there is data that was recorded to show that there was deformation, downslope deformation of this slope. And sure enough, from the surface reference rows that you see here, there was data that was showing in every event there was an accumulation of deformation, vertical settlement, and horizontal downslope deformation. In this 1985 event, the vertical settlement was of the order of 1 foot near the crest of the dam. So it really is a substantial amount just from one earthquake event. In addition, because of the availability of the inclinometers, you see that also the inclinometers were not only showing the amount of displacement at the surface of the slope, but also within the slope. And you might be able to see a hint of a place where there might be some evidence of a slip surface, but you also see that the deformation is distributed within the body of the slipping zone, different from our typical logic of a rigid sliding block. This data set remains very useful, and there is still much that can be gleaned from it even today. In the early 90s, I was searching for industry matching funds for a National Science Foundation grant that I had received. And after lots of search, the nuclear industry, and in particular EPRI, came to the rescue. Not only did they provide some funds, but they actually provided data sets that really became a cornerstone of almost everything else that I did from there on. And these data sets were recorded from a large scale experiment that they had funded. Many countries, as you see, were part of this undertaking. And it provided data on the response of the structure, but also of the soil underground in the form of what is known as these downhole arrays, which are accelerometers and pore pressure transducers that are installed within the ground. And as you see here on the left, this is just a schematic of accelerations and pore pressures that can be recorded from a downhole array. And on the right side is what we did with these accelerations in a very simple and straightforward way, calculating the shear stress from the recorded accelerations. The shear at any depth is just, for example, as you see here, the average of accelerations between the two stations where there is a recording. And also by integrating the accelerations, we get displacements. We divide the displacements by the spacing. We get shear strains. Shear stress versus shear strain, the holy grail right there from these acceleration records. So I meant to mention that actually this logic of the shear stress dependence on acceleration, of course, was employed much earlier by Seed and Idris in their liquefied simplified procedure, calculating the shear stress at depth multiplied by a stress reduction factor. On account of that, there's no downhole accelerations available. But this has really started with their good work. So from the recorded accelerations at different depths, you see that we can backfigure stress versus strain for the entire time history of the earthquake event in the east-west and north-south directions. And then we can select loops of different sizes, different strain levels, to see the change in stiffness and the change in damping as a function of shear strain amplitude. And as you see here, we summarized our data points and compared them with data at the time that was also available from the University of Texas, where they had extracted high-quality samples and reconstituted the samples and tested the samples in their lab. And this green bands is a comparison between the two data sets. You see that shear modulus is a bit lower. Damping is actually noticeably higher. But it's still validated that laboratory testing is very useful and shed additional light on things that we would just not know. If we only had the data from the lab, we would just use the data from the lab. We don't know that, for example, what actually happened was showing more damping and so forth. EPRI also had an additional site in Taiwan where they had instrumented, also with downhole instrumentation, a very stiff site. So Lotang was a soft soil site, and Hualien was a very stiff soil site. When we started doing our analysis with the data, trying to just back calculate shear wave velocity profile, we kept on finding that X and Y direction shear wave velocity profiles are not the same. One of them is noticeably stiffer than the other. And you know, when you get something that you don't expect this way, you keep on going back and forth and checking your code and checking your analysis method. And then finally, we found a publication by Professor Luco where he did all his analysis on the response of the superstructure, on the response of that nuclear containment structure, the 1/3 scale nuclear containment structure, and independently, without any of the data recorded in the soil, came to the conclusion that the only way to explain the recorded response was that there must be an azimuthal anisotropy in that the soil in one direction is stiffer than the soil in another direction. So even though earthquakes don't happen every day and it is costly to do site instrumentation, you can see things that you will never guess might be happening from actual data as opposed to just reliance on laboratory tests or physical modeling, or of course, computational modeling. So hopefully, more and more of these data sets will become available for people to learn from and benefit from. Once we started working in this direction of stress versus strain, we started seeing that we can apply this to physical models. People are doing lots and lots of centrifuge tests. They are doing lots and lots of shake table tests. And they put down whole arrays, essentially, in their experiments. And actually, for situations where they are tracking lateral deformations, on the right side here, you see that they also put displacement transducers. So not only do we get accelerations and we get excess pore pressures, but we also get displacements, which allows us to actually synthesize the whole lateral deformation, stress strain history at different depths between accelerometers and get the whole picture from the very top to the very bottom, how the shear strains were evolving at different depths and all the way to ground surface. You might see, for example, that near ground surface, the accumulated strains are low because, of course, there was liquefaction at depth, which isolated the layers near the ground surface. And environments like this, of course, were really amazingly useful for calibration of computational models. Without this kind of data, you're only relying on sample tests for large strain deformation. And the information that you get here about the response of a whole site is just invaluable. And of course, from there on, I would say hundreds of experiments have been analyzed partially by this technique of stress versus strain. This is another example from a test at UC Davis, where we were looking at the response of saturated, very dense sand. And saturated is a very important word here because this causes, this sand is highly dilative, and with the saturation, suction kind of, if you will, happens, and we get this banana-type loops at very large strains. So at small strains, you see that the loop is the shape we expected, stress versus strain, but at large strains, it starts taking this shape. And because of that, if you do the G over G max curves back-figured from the recorded accelerations again, you see these shapes where instead of the usual reduction in shear modulus with shear strain, it actually levels off because the loop starts getting stiffer, and the damping at the same time levels off and in fact starts decreasing because the loop is getting thinner and thinner as the size increases. So I wanted also to bring up something related to pore pressure sensors. Of course, pore pressure sensors tell us the excess pore pressure buildup in an experiment, but also from these sensors, if we subtract one value from the other, we can estimate a hydraulic gradient, which can tell us the direction of water flow. And this particular experiment was selected because, as you see here, there is a potential for water to flow from the one side to the other side. And for that matter, in this schematic, if you shake the one side only, you get artesian flow, and it can increase the pore pressures on the other side and lead to a sand boil appearing on the other side, as you see here in this conceptual experiment. So the LEAP project, as you know, has really been an excellent project for the centrifuge community, and it's still ongoing, hopefully. where they have done experiments of that type with a sheet pile on one side, and so it was a very good opportunity to look at this mechanism. So we're zooming here on the excess pore pressure sensors, and this is data that was recorded in this RPI experiment number 13, excess pore pressure data at all the locations where there was a pore pressure sensor, the red dots. And so if we just go and apply this simple logic, it is simple, not very accurate, but informative, to calculate a hydraulic gradient based on the difference in excess pore pressures divided by the spacing. You see that we get pictures like this at different time instants. So this is at 17 seconds of shaking, 18, and so forth. And the interesting to see, of course, is that the water near the ground surface, of course, is escaping upwards. So you see the water escaping upwards. But near the sheet pile, there is some water trying to move towards the sheet pile as the sheet pile is moving away and yielding. But the most important thing is, as you see here, water is flowing from the left to the right. Water is flowing from the left to the right, finding that it's easier for it to escape this way, and consequently, it contributes to the excess pore pressures that happen on the right side, even if the soil on the right side wasn't planning to liquefy. It was very dense and wasn't planning to liquefy. All of a sudden, it gets this flow from the left side that is causing increases in pore pressure. This is a computer simulation just to further elucidate the mechanism. So as you see here, this is the same happening, the water going to the other side. But also here, this is a case where we increased permeability of that lower layer by 100 times, like a gravel or something. And you see now the arrows for velocity are so large, the water is now finding it is much easier for it to escape on the other side than to travel all the way up here to escape. And certainly that would lend itself to higher excess pore pressures on the right side. So possible relevance might be for situations where uneven topography, like sheet pile walls, slopes, dams, as you see here, and maybe some other scenarios. It's an interesting topic to look at further, in our opinion. Okay, let's do something about sensors that are just based on vision, that just are based on looking at something and seeing what is going on. So some years ago, again, inspired by work of others, we thought to get a test tube, fill it with sand and water, and then just raise it and drop it suddenly to the ground, whereby it immediately liquefies all the soil that is in the test tube. And so what you see here is before the impact, and then upon impact, the soil is liquefied. And of course, the liquefaction happens instantaneously, so it's not something where pore pressures are building up, but they're dissipating at the same time. It's just all immediate upon impact. And then after that, solidification starts, and the excess pore pressures start dropping, and the particles are in suspension as they push the water out of the way, as you see in this schematic. So, of course, there is always a lot of interest in stratified sites, sites where permeabilities are not the same or other soil properties are not the same. So I picked these videos to show you quickly about a scenario where we have this tube was transparent, of course, 1.3 meters in height, and it had a sand of higher permeability compared with a silica powder here, where the sand permeability is 60 times approximately more than the silica powder. And then we drop the tube and we start monitoring what is happening at the interface between these two types of soil. Of course, the idea is that this material settles very slowly because it has low permeability. This material settles very fast. So, and we're looking at this location, which is the interface between them. So this is the silica powder, this is the sand. Here we go. If we look at the video on the left, you will see that a water lens is opening up. So the sand is settling fast. The silica powder has very low permeability, and it opens this water lens, water is trapped, and then several seconds later, the water lens has become this big, and then just with very, very mild disturbance, you will see what is going to happen now on the right. The upper material starts collapsing into the water lens. If there is any shaking from an earthquake, it would have collapsed, as you see here. And actually, essentially, a sand boil is coming to life from the video, as you see here. So some of the interesting things that we can see from this test is while this process is happening, the void ratio actually exceeds Emax according to ASTM. This is just material that is floating and falling into this open space. Even after sedimentation, or the Emax is, the actual E is probably still higher than the Emax, the way ASTM says that we should do Emax. The water interlayer in this case, even though this here is low permeability, it's highly unstable, and the post-liquefaction permeability became much higher. And so if someone is doing a computer simulation of this upon liquefaction or post-liquefaction, they probably want to use a much higher permeability than the actual permeability of the layer. Another case was a case of a 3-layer, as you see here, where the transparent tube was 2.3 meters in height. And we had the silica powder sandwiched between two sands, as you see here. And then we're looking at that location where the silica powder is. And as you see, immediately upon impact, the collapse of that silica powder starts because the sand below it is just settling too fast, and we get this mechanism that is kind of similar to what happened in the 2-layer system. However, you see here it's continuing, but you start seeing that there is part of that silica powder that isn't letting go. And in fact, many, many seconds later, it's still there and wasn't planning to go away. So you see almost nothing happening here in the third video on the right because it was going to stay. And it stayed all the way and settled very, very slowly till finally the water lens closed up many, many seconds later. So from this logic, it appeared that this upper layer was a very important mechanism to keep this fine layer with its low permeability intact and not collapsing. Basically, what was happening is that the upper layer has higher permeability, and so it's actually pushing down on the silica powder and keeping it intact this way. That's why part of the silica powder that is feeling that additional pressure from the upper layer did not collapse and did not fall apart. So a 3-layer system like this gives you something very, very different from the 2-layer system, has consequences for potential lateral deformations, has consequences for what is the actual permeability, and these are all things that depend on thicknesses of the layers, permeabilities of the layers, and locations of the layers within the soil profile. So I couldn't resist this temptation related to stratification to go back and visit the wildlife site, which we had visited long ago, looking at stress versus strain also from a downhole array that was at this location. As you see here, 2 instruments, 7.5 meters apart, 2 strong motion accelerometers, 7.5 meters apart, and 4 excess pore pressure sensors. Some of you might, of course, be well aware of this, but as you see here, the accelerations at ground surface showed these peculiar spikes that also coincided with drops in excess pore pressure in some of the recorded pore pressure sensors. So from this analysis, we just divided to get a strain, we got an average strain divided by the spacing of 7.5 meters between the 2 stations, and we found that what we end up with is this kind of stress versus strain with the time axis here showing stiffness and then loss of stiffness, maximum strain of 1.5%. So if we look more carefully at the data from these excess pore pressure sensors, you find that the upper two that are beneath that silt layer, which is of lower permeability, show the spikes. In fact, that one that is closest to that interface shows the most spikes. That one that is a little bit deeper, only half a meter deeper than this one, you could just start seeing traces of the spikes, but they're still there. But if you go to the excess pore pressure sensors that are at depth at 5 and 6 meters, you don't see any evidence of any spike in them. So it kind of suggests that actually the large deformations really were concentrated to a great extent in that zone, because by the time we were here, there was hardly any dilation happening. So the deformations really were taking place in that upper half meter. And there is a water-rich layer or a lens here of water that was evolving. And in fact, there is evidence that there were sand boils at the site, which is also something that is related to stratification. And consequently, that 1.5% is very likely much higher, since now the deformations are concentrated right below the silt layer at the very top of the liquefied layer, and might be as high as 10 or 11% if you divide by a spacing of 0.5 meters or 1 meter instead of the 7.5 meters depth. Okay, very quickly, I wanted to touch on a situation of sensor networks for soil structure interaction. Of course, this could be a presentation of its own. There was this scenario at Eureka, California, where there was instrumentation deployed on several bridges, and the downhole array also at that location. The bridges, as you see, are half a kilometer long, 3/4 of a kilometer long, and the instrumentation is all around at the top of the structure, also in the soil and the downhole. And also, when they were doing a retrofit, they installed accelerometers inside some of the piles in the ground. So it was really a great opportunity also to see what are the pile foundations underground doing. This is here the pier that was instrumented, E7, and the instrumentation underground. So from the analysis, there were only mostly weak earthquakes and one moderate level of shaking earthquake. So from a study of optimization to get the best possible response from the data that is available to us in the ground, we back calculated lateral stiffness of these pile foundations. This is the plan view of each set of pile foundations under each pier. And we found that in the small earthquakes, lateral stiffness, for example, in this zone, is that where the piles are nearly totally embedded in the ground, is about 500 meganewton per meter. And then when we went to the one single moderate shaking event that had a peak acceleration of 0.25 G, this stiffness dropped by more than 3 times, as you see here. So even for a very relatively weak event, you see that the stiffness drops by a very substantial amount. Another bridge there, the Samoa Bridge, again showed the same thing since time is tight, but you see again in the event that was the moderate event, lateral stiffness, again, of the systems that are embedded in the ground, 500 versus 120, almost a factor of 4 or more. So with all this data, ground response alone, soil structure interaction, of course we are looking to have simulation tools that can be calibrated on this basis, and then from there we can use these tools for prediction of response under other earthquake scenarios. So side by side we were working on that, developing models, incremental plasticity models for cyclic loading, some for granular soils, and we adopted the UP formulation of Chan so that we can look at liquefaction, flow liquefaction, cyclic mobility, lateral spreading. Each one of them required special handling, so to speak, so that we can get the response that we were observing. But with all these things that also work in 2D and 3D, a great opportunity came to integrate all these models into the Peer Open Seas framework. that was really a great opportunity for us. It brought into the picture the very useful nonlinear elements also for the structure, very powerful computational tools to do the analysis. And it is something that, of course, as you all know, widely employed worldwide. And we were very happy to be among the early contributors in this package. And of course, since that time, many, many great pieces of work have been done by others and are being integrated into this platform. When we started thinking, we have these three-dimensional tools, we want to do something in 3D. Life is 3D. Bridges are a 3D structure, shaking X, Y, and Z, and so forth. So we started looking at simple 3D scenarios. One of them was this scenario that you see here, where ground modification is done in the form of cells, as you see here. So if we use the periodic boundary logic, we can do three-dimensional analysis of ground modification. Gravel drains, stone columns, pile pinning, deep soil mixing, and many others. Very simple mesh, runs very fast, almost as fast as running a one-dimensional analysis, but you're doing things in 3 dimensions in a very convenient way. We even put together a user interface to do the pre- and post-processing and get the results for, like I said, a myriad of ground modification methods. After that, of course, we are looking for simple environments for 3-dimensional analysis. Another one that surfaced was the situation of a wharf. As you see, the wharf extends this way, but in plan view, it is supported on piles in a pattern that repeats itself, which allows us to take a slice and study the wharf problem on pile foundations in that form that you see here, with a 6-meter wide 3-dimensional slice between the pile foundations. As you see from this analysis, when the slope moves, it deforms horizontally, but also deforms vertically. And typically, our main attention is given to the horizontal deformation. But in this case, we saw that the vertical deformation, the ground is heaving up near the toe of the slope and settling in the back. And so uneven vertical motions are happening, and the poor piles are all connected to this rigid platform, which is the wharf at the top. So they can't move individually to accommodate this. And in return, you see very large changes in axial forces happening in the piles. So what I would say, these are just representative, but it's something that would make us really hopefully think more about what are the axial forces that might happen when there is lateral ground deformation or when there is a slope deformation this way for wharfs and for pile groups, because again, the pile groups are spatially distributed, and you can have positive and negative forces acting on the pile groups as well. Something that probably is contributing to the damage that we have been observing, but typically most people would still attribute the damage to horizontal deformation more so than vertical. The slice logic also helped us to look at bridge systems this way and bridge ground systems. Again, we took a slice here in this 200-meter long bridge to look at mechanisms of response that stem from overall system response, from modeling the whole bridge as accurately as you can from the structural point of view, connecting the soil to the bridge elements by these zero-link things that allow us to do axial force interaction and horizontal force interaction. And after the shaking, for example, in this case, first of all, you notice that there is a permanent ground deformation that is affecting the whole domain, not only deformation from slope deformation on the left and on the right, but there is a lurch to one direction just because of the nature of the motion that was used as excitation at the base of the mesh. And that actually contributed in the end to the deck moving forward about 20 centimeters at the top, whereas when that slope moved backwards, if you will, or in the other direction, you get a double curvature here on the piles on this side. Of course, you get lateral spreading forces on the piles on the left side, but also interestingly, somewhere in the middle, there is very little soil movement right and left, but because the deck has moved 20 centimeters, that also has caused trouble for the piers in the middle. The piers in the middle are not suffering because the piles have moved, but they're suffering because the piles have not moved, but the bridge itself has moved because of that lurch and because of the mechanism of response associated with it. Similar situation arose when we looked at, this is a 100-meter long bridge in a narrow waterway. It's supported on steel piles in this case. And you see here that the deformation of the left and right slopes interact at the middle, and they actually get in each other's way. And the final deformation, which was 0.65 meters maximum, if this was studied as one slope at a time, it would have resulted in 5 meters of lateral deformation estimate. So that also was a nice, insightful thing to see that really ought to be part of analysis of systems where the waterway is narrow enough that it inhibits deformations on account of that. This is just a quick slide because I mentioned that we integrated everything with many, many peer researchers, and consequently, the tools are being used today also to calculate repair cost, repair time, and carbon footprint, as you see here in this schematic. So quickly, let's see, what did we learn? So we are seeing that we can do much better three-dimensional simulation of simple scenarios like the slice model and the ground modification model. We are seeing that axial deformations need to receive more attention for pile systems, not only lateral deformations and bending moments. This method of interaction between the soil elements and the pile element has worked okay for us, but still needs a lot of additional work to look at scenarios of gapping, liquefaction interaction, very high strains that the soil suffers as it interacts with the pile, and so forth. Down here is the idea of that equivalent linear analysis, which used to be the generation before plasticity and so forth, actually can still be done in the time domain. It's done in a different way, not exactly like the old one, but can still be done and can be very effective in one-dimensional as well as 2- and 3-dimensional analyses. And I wouldn't give up on it. Being in the business of plasticity for all these years, when I saw that something simpler can give us a good answer for situations that are not liquefaction, of course, but it can be useful, so I thought I'd bring it up. And then the other thing to keep in mind is the system response and the interaction of the slopes whereby the bridge experiences axial forces into the bridge. And so when we saw this, the idea was, why don't we use the deck of the bridge as a strut between the two sides of the slopes? Of course, the bridge has to be designed in a different way, has to be designed to start with, to be ready to handle these axial forces, but it can be a very, very effective mechanism of reducing deformations on both sides for free, in a sense. No ground modification or additional work done, just push one against the other and get much less deformation. We touched on that point of that in the middle of the waterway, there is a zone that has very low deformations. That is something also that can possibly be included in simple slope analysis, where here we put a barrier for deformation, we just truncate the slope, or we do something else in a finite element model and get much more realistic deformations compared with the study of just a slope, in the classical sense. Another thing that I would like to share with you, and that's really our own thinking at this point, is that when people have a loose layer here for liquefaction, the typical ground modification that is done is that they strengthen all the way down to the good soil, so to speak. So in that case, this loose layer is 10 meters in thickness, is 9 meters in thickness. And one way of doing ground modification is to strengthen under the surface load all the 9 meters. The other thing is to strengthen only 8 or 8.5 meters and leave a half a meter of this loose sand in place. Do not strengthen it. So if that loose sand actually liquefies, it will act as a natural base isolator and potentially can reduce accelerations in a very substantial way, which is what is shown here in this acceleration record. You see when the 9 meters are all strengthened, the accelerations reach 0.5 g at the base of the structure. With this half a meter that is left untreated, accelerations drop by a factor of 2 or more. This is the red part. And of course, for the fully liquefied scenario, the accelerations are very little because of base isolation. But you also get tons of accumulated settlement without ground modification, and you get much less settlement that probably can be tolerated just by leaving this little bit of material under the remediated zone. So if you're still worried, you might buy into the logic of the thickness above the liquefied layer versus the thickness of the liquefied layer. So this is Professor Ishihara's work. So if your layer that is liquefied is only a half a meter in thickness, you're down here. And for any thickness of layer above it, there is not going to be any damage. Also, I thought I would bring this up that Professor Idris, also looking at response of soft soils like bay mud and so forth, also suggested that the acceleration might better be capped at a value of 0.6 g, for example, and not just keep on increasing it based on equivalent linear analysis or other types of tools, on account, again, that soft soil actually reduces peak accelerations. This is just another scenario, a different earthquake showing the same exact thing, high accelerations versus low accelerations, and high settlement versus low settlement. Of course, we all understand that we need also large deformations, which many of us have shied from. We have focused on the plasticity of the soil and so forth. Large deformations still remain a very difficult problem. This is here a step in this direction. Many other people are doing even more advanced work than this, but it's something that we want to keep in mind and continue refining. I wanted also to share with you something that we ended up feeling that we had no choice, but we had to do this to get realistic response once the soil liquefies, especially for the lateral spreading situation. So let's say you see an experiment and this is the response. This is the yielding before dilation starts. This is the cycle by cycle yielding. And you're trying to get your model to reproduce this response when your confinement, effective confinement is essentially 0, and the shear stresses are super small numbers, under 2 kPa or whatever. And in this location, when we're trying to go from contraction to dilation based on a phase transformation line, it was a joke. We weren't ever getting anything that was reliable, that we could really calibrate in one scenario and then use for another scenario. So in the end, we found that why don't we actually introduce these parameters as strain space parameters in the stress space constitutive model. So these are user-defined values that will actually make the model reproduce what you want it to reproduce. You see, this is what you want to get, just ask for them. Ask for them in the model. So that isn't done by too many models. It's a workaround, if you will, but allows you to have a much better opportunity to actually reproduce observation or reproduce a desired outcome that you are looking for. And I'm seeing gradually, especially lately, other ways of people where one way or the other, they're starting to bring these strain space parameters in their modeling environment. Okay, so we thought, we won. We are reproducing the strains that we are observing. But actually, when you put this in the computational framework, and now the stiffness is gone, the damping force pops up as a very large element in the overall response and starts getting in the way. So for example, this is a run here with the classical damping that we were using during the dynamic run was working very well, and it didn't show any large deformations after the layer liquefied here between these two zones. And then we started looking at, well, what do we do? Do we use mass proportional damping? Do we use a combination of mass and stiffness proportional to get this flow liquefaction taking place? And eventually, the short answer is, yes, you need a very special treatment of damping once the soil liquefies. The damping that you were using before liquefaction, dynamics and so forth, isn't necessarily going to work once the soil liquefies. Another thing is related to near-field motions. We've becoming more and more interested in assessing damage. When the large one happens in Los Angeles, the large earthquake, the magnitude 8 earthquake, the magnitude higher earthquake. So near fault, these earthquakes will come with significant permanent displacement. Our acceleration records today, even the ones that we call near fault, of course, are baseline corrected as usual, and they lose this component of permanent deformation. That still works for many cases, but for cases where the ground is liquefying or you have a very soft layer, the outcomes can be significantly different if you have the permanent deformation versus not having the permanent deformation. Luckily, GPS and satellites are increasingly helping us. And even today, there is enough data that we can go back and make corrections on some of the acceleration records in recent earthquakes that we have recovered that would include that permanent deformation component. But this is only something that will increase with time and will become hopefully part of our mainstream analysis. Finally, I've been hearing, like all of us, about AI tools. So I went to Gemini, which is the AI tool of Google, and I asked it to compose a song about soil liquefaction. And this was actually the first iteration. I didn't take it and put it back in and ask it to improve it or anything. This is what it came back with, as you see here, verses about that the ground beneath a solid frame, so it's starting, to describe the tremors. And then after that, it goes to say the water trapped finds sudden space. Very good logic. And then after that, it goes to liquefaction, a silent threat. The engineers, they strive to know the behavior. And then, but knowledge gained, a watchful eye can mitigate the danger high. So not only did it give something that rhymed, but it gave something that had an introduction, a body, and a conclusion. And so I was so impressed, I asked it to sing it. And then it gave up. It said, I can't sing, but I can generate some music, and it gave me this back. And it made some additional good suggestions. Okay, I hope you enjoyed this presentation. Thank you very much. I'm very grateful.